Okay, we can look at P1 matter. We can look at how substances heat up, what happens to them when they increase in temperature, and we're going to look at what happens to them when they cool back down again. So this relates to the particle model. We've looked at this before, but let's just recap it. So if we start off with a solid, okay, we're going to draw a quick particle model. Keeping those particles the same size. They start off in fixed positions. The particles vibrate about fixed positions. Okay, so that's our solid. Okay, if we increase the temperature enough, eventually we will melt, and we will have particles in a random arrangement, but still in contact with one another. They are now able to flow around one another as a liquid. Okay, so we've got a random motion. We've still got contact, but they can flow. If we increase the temperature a bit more, okay, we can end up with a gas where the particles have completely overcome the intermolecular forces, and they are moving about at random speed and random direction. Okay, remembering that between each particle there is nothing. Okay, so 3 states of matter that we need to worry about: solid, liquid, gas. Between the solid and the liquid we've got a change in state, that's called melting. Between the liquid and the gas, we're going to call that boiling. Boiling, if we're actively heating it. You might describe that as evaporation if it's more passive, but I'm interested in its boiling point. Okay, so I'm just going to describe the change from liquid to a gas as boiling. Okay, what does that look like as a graph? If we draw some axes here, look at me using a ruler. Okay, I've got time on the x-axis. Let's give it some units. Let's say it's in minutes. We've got temperature on the y-axis. Let's say we've got degrees Celsius. Okay, I can increase the temperature of a solid. Okay, but when it gets to melting, the temperature stops increasing. Then I can increase the temperature of my liquid, but when I get to changing its state, when I start boiling, the temperature stops increasing. Then I can increase my temperature of a gas. Okay, and I probably curved that over a bit too much. I can carry on increasing the temperature of my gas. Okay, so we need to remember, okay, that when we've got a change in state going on, the temperature stays the same until all the particles have changed state. Okay, so this area here is our melting. Okay, the temperature stays the same. This area here is boiling. It's a state change. The temperature stops increasing. Okay. Now these temperatures are specific to the substance being heated up. Okay, so for example, if this was water, if it was pure water, this would be at 0 degrees, and this would be at 100 degrees for pure water, because that's a property of pure water. Okay, substances have specific melting points, they have specific boiling points. We can actually identify a substance by its melting and boiling point. Okay, if I had some water and it melted at a slightly different temperature to 0 degrees, I would suggest it had some contaminants in. That's why we add salt, for example. Okay, so we add salt on, we put salt on the roads. Okay, so that the ice doesn't form until it's really cold. Okay, we don't want ice at 0 degrees. It's often 0 degrees Celsius outside on a winter's day, and we put salt on the roads to stop it from forming ice. until much colder temperatures. Okay, so that's what heating up looks like. Okay, we start off with a steeper gradient, it tends to sort of curve off. Okay, as the temperature difference between the substance and the surroundings increases, it gets harder to increase the temperature because if the energy is being transferred to the surroundings. Okay, so let's have a look at cooling down then. So when it comes to cooling down, I kind of get the reverse going on, but there is a slight change in what the graph looks like. So let's redraw this. Okay, so I've got my gas particles. In reality, if I was drawing this particle model to scale, there's no way you'd see these gas particles this close together. Okay, they should be drawn much further apart than that, but I want to fit them on the page, obviously. Okay, I can condense my gas to a liquid, so they go down into a random arrangement but each one is stood in contact with another. Okay, because those particles are attracted to one another, and they've now got intermolecular forces keeping them together as a liquid. So if I keep cooling it, okay, gases can flow as well, by the way. Okay, we described that as flow. It's the contact between the particles that's important. That's the big difference between a liquid and a gas. Solid, we've got that fixed, regular arrangement of particles. Okay, now we're in fixed positions. Solids can't float. Right, so let's draw that as a graph. I've got my y-axis is going to be my temperature again. X-axis is going to be time. Let's have my units on there. I think we had minutes. So we'll have minutes again. Okay, so let's say my gas, I started up here, I'm going to cool down quite rapidly because there's a big difference in temperature between the gas and the surroundings, so it's going to cool down and then level off during the state change. Then it's going to, once it's changed state fully to liquid, then I can cool my liquid down. Okay, and then it's going to level off and then I can cool my solid down. Okay, so I've got, once again, I've got a level horizontal part of graph, horizontal section where the temperature does not change. Okay, that is going to be my condensing state change. Okay, so I've got cooling here, I've got condensing here where the temperature is level for a period of time, then it can cool again until we get to a temperature where the substance freezes. Okay, and then we can do more cooling. Now, if this was water, as we had before, this would once again be 0 degrees Celsius because the melting point is the same temperature as the freezing point. Again, for water, if I was condensing, it would be happening at 100 degrees Celsius because condensing happens at the same temperature as boiling. Okay, so if these were my temperatures, I'd be thinking this must be pure water. Okay, and that would be pure water at sea level. You can look up why, or you might have an understanding why. You can look that up yourself. Okay, so the graph looks slightly different. Okay, the decrease in temperature is rapid and it starts to level off. That's what a typical cooling curve would look like. Okay, if we're trying to heat something at a different temperature to its surroundings, cooling looks like this. Okay. And heating looks like this. Okay. temperature decrease is rapid here because we're at a very different temperature to the surroundings. This is less rapid here as we approach the temperature of the surroundings. Now this graph here, I should point out that it's going to cool down until it reaches the same temperature of the surroundings. So imagine this was a beaker with water in the air or a cup of tea. It's going to decrease in temperature until it is in equilibrium with the surroundings. It is at the same temperature as the environment. So we might say that this temperature here, that would be room temperature. So heating and cooling, these two particular graphs, there's no state change here because at no point does it level off. Okay, so this is just maybe heating some water, and this is maybe cooling that water in a room environment. This one isn't quite, I should have probably started that at the same temperature. Okay, if we're going to start heating some water in the room, it's going to start off at the room temperature, isn't it? So beware, you might be asked that in an exam. You know, why does the temperature not start at 0? Because we need to remember we've got room temperature going on, and so we'll be starting at room temperature. Maybe that would be about 20 degrees, 21 degrees, something like that. So in terms of what equations can we use on graphs like this, well, if there's a change in temperature going on, it's written on an equation like that, that's a change in temperature. This means change in, that is used to represent temperature. The only equation on your equation sheet that has that in it is this one. The change in energy, or the energy transferred to our substance, or from our substance, equals the mass of that substance multiplied by the specific heat capacity multiplied by the change in temperature. So we're going to use that equation where there's a change in temperature. That's only going to be useful for these parts of the graph where the temperature is changing. Okay. Likewise, if we're going to the heating up graph, okay, this equation is only useful for when there is a change in temperature. If the change in temperature is 0, then we're not going to have any value for E, are we? So if this is for heating and cooling, okay, that's our mass, which we could measure with a balance. Here's our specific heat capacity, okay, and this is our change in temperature, which we could measure with a thermometer, and this is the energy transferred. And we could use this equation for a substance being heated up or cooled down. Both of those situations have a change in temperature. For the change in state, where there is no change in temperature, okay, there's two parts on this graph, okay, we're going to use this equation. The energy transfer can be calculated by the mass of the substance multiplied by the latent heat of fusion in the case of cooling, or the latent heat of vaporization in the case of heating. Okay, so there are two equations that you might use for the heating and cooling of a substance. This one is for if there is a state change going on. Okay, so you've got two equations for the different parts of this graph, so be aware of that. Alright, they will give you the value of the latent heat of fusion or vaporization, or they might be asking you to calculate that. Alright, you just need to be aware of these two equations and know how to use them. Alright, and I'm going to leave it there. Alright, thank you.